Three, two, one. All right, here we go. Let's go. I'm very excited because now it's time for us to move into chapter 1 officially. Well, I guess we kind of already started getting into chapter 1, but it's time for the star of chapter 1, which is, of course, the set of real numbers, which will be a set that we will grow to love and know very well for the remainder of this course. All right. So again, this is our fundamental set. It's the set of numbers that we've worked with in our entire life with calculus. Now, we have all of the tools we need to formally describe it. It is an ordered field with the least upper bound property. So it has addition, it has multiplication, it has ordering, and all three of those behave the way we think they should. Addition does what addition does, multiplication does what multiplication does, and ordering does what ordering does. And the key ingredient that makes the real numbers the real numbers, and different than the rationals, is the least upper bound property. Alright, well, why is that right? Why is that correct? Right, why is this the definition of the real numbers? So that's going to be our goal for today, is to begin answering that. And our first goal is to establish that the integers and the rational numbers are present in the set of real numbers, and they behave exactly as we expect them to. So the integers have some key properties to them, the rational numbers also do. And that'll be our first goal for this first part of talking about the real numbers. Our second part of talking about the real numbers, which will be in our next video, we'll talk about the irrational numbers. We'll get into the why there are other things in the real numbers, and that's where the least upper bound property comes in. Although we will see the least upper bound property in action today, telling us that integers do what you think they should do. Alright, before we begin the process of getting into that, let us note that the zero element and the multiplicative identity element, that's 0 and 1 as we know them. Right, 0 adding it to anything doesn't do anything, 1 multiplying it by anything doesn't do anything. So 0 and 1 are now officially 0 and 1. But let's start getting the other numbers. So first we're going to go after the natural numbers. So a subset of the real line is called a successor set. If it has 1, and given anything in the set, 1 plus it remains in the set. Sounds a lot like induction, doesn't it? Yeah. Ooh. Alright, so note, the real numbers themselves have this property, right? 1 is a real number, and adding 1 to anything keeps us a real number. So because the set of successor sets then is non-empty, we can intersect all of them, and that's what the natural numbers are defined to be, the intersection of all possible successor sets. Okay. And in particular, this definition is going to allow us to prove the following facts. The natural numbers are contained in any successor set, and the natural numbers themselves have the property that 1 is in there, and if you have something that's a natural number, adding 1 to it remains a natural number. So in other words, what we're about to prove is that there is a smallest subset of the real line that has these two properties. Probably, you know, the set 1, 2, 3, 4, so on and so forth. Alright, so let's establish that the set of natural numbers indeed has these two properties. So if you take a natural number, well, by construction, it has to belong to a successor set, because it's the intersection of all such sets. So if you're in the natural numbers, you're in any successor set. So the natural numbers are a subset of any successor set. All right, let's prove the natural numbers themselves have that property. So first thing to note is that 1 belongs to any successor set, so it's in the intersection, so it's a natural number. All right, well, now let's say we have a natural number. We want to prove that n plus 1 is in there. Well, for any successor set, n must belong to it, and by the property of being a successor set, adding 1 to it keeps you in the successor set, so n plus 1 belongs to every successor set. That's precisely what it means to be a natural number. So, the natural numbers are contained in any successor set, and they themselves are a successor set, so they are precisely the smallest possible successor set. Okay, and now equipped with this, we prove that the set of natural numbers is precisely what we think it should be, what we have in our head. It's the numbers consisting of 1 or 1 plus some other natural number. So no, we couldn't define the natural numbers to be the set, right, because this is recursive in a way, right? You're a natural number precisely if you are 1 or you're 1 plus a natural number, right? You couldn't just start off with that as the definition, because that definition, right, is based on itself. But establishing the set of natural numbers as the smallest successor set allows us to prove this. So what do we need to prove? Well, I want to show that anything that's a natural number is either 1 or 1 plus some natural number. Well, let's let S be the following set. We'll prove that this is a successor set, and thus, since X is a natural number, it's belonging to the successor set, which means that X has to be 1 or it's a natural number plus 1. Okay. So the set of natural numbers then is precisely the elements 1, 1 plus 1, 1 plus 1 plus 1, so on and so forth. Alright, okay, so first things first, obviously, as 1 is equal to 1, it's in the set S. Alright, now to take something in the set S, I need to show that it is either 1 or it is a natural number plus 1. So if S is in the set, that means it's one of these two things. I want to show that if I add 1 to S, then one of these two things happens. Okay, so two possibilities. Either S is 1 or S is n plus 1 for some natural number n. Alright, well, in the former case, if I add 1, then I get 1 plus 1, which must belong to S, because 1 is a natural number, and S plus 1 is 1 plus a natural number. And in the latter case, S plus 1 is n plus 1 plus 1. Well, n plus 1 is a natural number, because n is a natural number. Again, n, the set of natural numbers, is a successor set. Alright, and so there we go. Regardless, we find that S plus 1 belongs to our set S, so that means S is a successor set. And since X is a natural number, it must belong to that successor set, and thus X is either 1 or n plus 1. Alright, and so as we claim, this guarantees that the set of natural numbers is precisely the set consisting of 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1, so on and so forth. So all of the natural numbers are in our set. Yep. And as per usual, we rewrite these. So 1 plus 1 is 2, 1 plus 1 plus 1 is 3, 4 times is 4, so on and so forth. So the set of natural numbers exists, it lives in the set of real numbers, and it's precisely the set you think it should be. Now, it's worth noting that arithmetic will be taken for granted. Now, the old joke is that it took mathematicians 500 pages to prove 2 plus 1 plus 1 is 2. That is not exactly what they're talking about. Is a document called Principia Mathematica, written by Whitehead and Bertrand Russell, and like that. Yeah, it takes them like hundreds of pages to get to arithmetic, but 1 plus 1 equaling 2 is just the definition of 2. You don't actually prove that. What you do prove is that 2 plus 2 is equal to 4, which you can formally prove by noting that 2 is 1 plus 1. The associativity addition allows us to move this over here. 2 plus 1 is 3, and 3 plus 1 is 4. So if you want to prove every arithmetical fact out there, you can, if you want to. But we'll go ahead and go, yeah, numbers add up the way that they always have added up. Nothing weird's happening there. Alright, so now that we've established the set of real numbers, let's prove the set of natural numbers. Let's prove what is without a doubt probably one of the most important facts of them, mathematical induction, meaning that if I have a subset of natural numbers, if 1 is in the set and anything n living in the set, then 1 plus is in the set, then it's got to be that what I have is precisely all of the natural numbers. Okay. Now note, the hypothesis here is that A is a successor set. So the natural numbers must be contained in it, but by hypothesis, A is contained in the natural numbers, so A must equal n. And now, equipped with mathematical induction, you can start proving all sorts of fun properties of natural numbers. So, for example, the sum of two natural numbers remains natural. Okay. So, since n is a successor set, that means n plus 1 is a natural number. Now, by mathematical induction, we've taken care of the first case, so now let's suppose that n plus k is a natural number for some k. Alright. Well, since n is a successor set, adding 1 to that keeps us in the set of natural numbers. So by induction now, it's got to be that n plus j holds for all j. Right, I showed that it works for 1, and then I showed that if it worked for some natural number k, it works for some natural number k plus 1. Beautiful. So that means that it's worked for all natural numbers, and since m was assumed to be 1, that means n plus 1 is an m. There we go, beautiful. So note, this is the way I like writing out inductions. I do not care about writing out, base case, induction hypothesis. No, like, even if that's how you were taught it, and that's how you like doing it, great, you can write it that way. No mathematician really writes it that way. Here's the base case, here's the hypothesis, we're done. That's all there is to induction. Induction is not a huge deal, it's a beautiful mathematical technique, and it lets us inductively prove a bunch of fun stuff. So, for example, again, our goal here is not to be exhaustive, or goal here is to be illuminating. There are plenty of other facts about natural numbers that you can inductively prove, such as every natural number is greater than or equal to 1. That's obviously true for 1, and then if you add 1 to both sides, it's still true. A product of natural numbers remains natural. I need an M there as well. And there's a bunch of other inductive facts that can be verified about natural numbers. But one that I want to explicitly prove, which tends up being a really powerful tool when we talk about integers, is the following. Which is the fact that we can connect the ordering of the real numbers to algebra in a very explicit way. So specifically, if I have two natural numbers and an m, and I know n is strictly less than m, then it's got to be that m is n plus some natural number k. Right, and again, that's sort of just like, you knew that before you clicked into this video that had to be true, but we need to prove this. And it's worth proving this because this is actually kind of a slick induction argument. These are pretty routine induction arguments, but this one is a little bit craftier. And like I said, this is a key fact for integers, so it's worth actually proving this. Alright, so we'll define the following set. The set of natural numbers p, so that given a natural number q that's strictly bigger than it, q is equal to p plus k for some k. I'm going to use induction to verify that A actually has to be the natural numbers. So note our conception of induction, which is if you've got a subset of natural numbers so that 1 belongs to the set, and if n is in it, then n plus 1 is in it, then A is equal to the natural numbers. So with induction, sometimes it really helps, especially when you're trying to prove something a bit more complicated, to actually just set up the set and show that, okay, by induction, this is all the natural numbers. So we'll first verify that 1 has this property, and then we'll show that if n has this, if some natural number has this property, then 1 plus it does as well. Okay, so let q be something strictly bigger than 1. Well, q is a natural number, and it's not 1, and we've already proven that the set of natural numbers are precisely the things that are 1, or are 1 plus some natural number. And note, that is precisely the requirement here. Right, so p in this case, the base case, is equal to 1, so replace this with 1 and replace this with 1, it's true. So 1 is in the set. Alright, now suppose p is an a, I want to show p plus 1 has to be an a. So take a q that's strictly bigger than p plus 1. Alright, now p is a natural number, which means that it's greater than or equal to 1, so we know p plus 1 is strictly bigger than 1, so that means q has to be k plus 1 for some k. Alright, well, plug that in here. That gives you p plus 1 is strictly less than k plus 1, so p is strictly less than k. Alright, since p is an a, that means k has to be p plus j for some j. And then now we go back to q. Q is k plus 1, k is p plus j, and there we go. We now know that q, which was strictly bigger than p plus 1, has to actually be p plus 1 plus some natural number j. So p plus 1 is an a, so a must be all of the natural numbers. So we now have this explicit connection between the ordering of the real numbers and the algebraic properties of the natural numbers. Beautiful. So, like I said, this was a bit more of an involved induction, so it's worth working through the details of. And also it's worth noting, like I said, that this is kind of a very fundamental fact about integers, not just natural numbers, so worth proving. Okay, now, before moving on, let's point out some things about induction that we're not going to dive too deep into, but if you want to, you can. Induction allows you to recursively define things. So, for example, the power of anything, so when I talk about a real number to the 12th power, what does that mean? Well, how do you get to 12? Well, you start with 1, and then you crank your way up. So we can use induction to recursively create this, because, right, I have a definition for 1, and I have a definition of how to get to n plus 1 if I know n. So with this, you can then prove a bunch of stuff about exponentiation, like base to power is base to the product of powers, and other similar facts that we'll just basically take for granted. But if you want to prove it, go ahead. So again, like I said, I'm not aiming to be exhaustive here, or just aiming to be illuminative. Something that we're going to talk about a lot more next, not next week, but the week after, which is series of real numbers. You can find series recursively, where adding up from 1 to 1 is just start with what you got, and if you want to get to n plus 1, you just add the next term. And something else that we've seen recursively is factorial, where 0 factorial is defined to be 1, and then to get to the next one, you add 1 by just multiplying by n plus 1. Okay, and now I'm sure there's some of you that have been cringing this whole time. And here's the rant. 0 is not a natural number. Fight me, you're completely wrong. If you're a computer scientist, you might be a little right, but you're still wrong. In analysis, we start things at 1. There is very rarely a reason to start at 0. With polynomials and power series, sure, you start at 0, but for most purposes, natural numbers start at 1. And if I ever need 0 to be there, I use n sub naught for that purposes. Now, this is just a weird point of contention. Some people would argue 0 needs to be a natural number because, right, when we're talking about the size of a set, the empty set has no elements, so 0 is natural. But in my opinion, no, everything starts at 1, and there's a lot of theorems here that we're going to see about natural numbers that really require them to start at 1. So I start at 1. And I feel like most analysts would agree with that, but other mathematicians might disagree. But again, for inductive purposes, it really does not matter where you start. You could start in a -1. You could start at -15. You could go to 5 or 6 stores. Or just 1. Alright, so let's actually prove something that, in my opinion, is one of the main reasons why I want the natural numbers to start at 1, and that's something called the Archimedean property, which Archimedes probably understood this, but obviously the Greeks didn't have algebra, so he wouldn't have written it this way, but... Alright, so what does the Archimedean property say? It says that if you've got 2 real numbers, 1 strictly positive, then there is a natural number, so that y is always less than or equal to n times x. And now note, if I allow 0 to be part of the discussion, this is not necessarily true, because if I multiply by 0 here, well, that forces y to be strictly negative, but my hypothesis here is that y is any real number. So so the Archimedean property, one of the many reasons why I think the natural number should start at 1. And now it's worth noting, we're finally actually going to use the least separate amount property of the real numbers here to prove this. Yeah. Now, note, what's actually going on here is this is just saying that if I have a positive real number x, then if I add it to itself enough times, it will be bigger than y, no matter what y is. So, that's all it's really saying. Alright, so let's prove it. So the way we're going to prove it is as follows. Let E be the following set. I claim the set's not bounded above, so that means there's something in it that is strictly bigger than y, right? Because if E doesn't have an upper bound, that means y cannot be an upper bound, so there's something in the set that's bigger than it. Strictly. Right, and again, remember, we proved that about upper bounds. Okay, so E, note, is clearly a non-empty set. It's got x in it, for example, so if it was bounded above, it has to have a supremum. Alright. Now, let's show that if it had a supremum, we've got a problem. And now note, I'm going to explicitly use the hypothesis that x is strictly positive, because if I take alpha and subtract x off of it, that has to be strictly less than alpha. Right, and you can go from here to here by, of course, right, you can subtract alpha from both sides and then flip the sign. Now note, alpha minus x is less than the supremum, and as we proved, the only things that are upper bounds are things that are bigger than supremum. So if I'm strictly less than my supremum, this cannot be an upper bound, which means I can find an element in my set that is bigger than it. Ah, okay. It's all coming together. All right, but now how do we finish it off? Right, where do we get the contradiction here? Because all I've done so far, right, is if I'm bounded above, I got the least upper bound property, it gives me a soup. My hypothesis here of strictly positive is being used. All right, and then now I know that can't be an upper bound, so now I've got an n here. Now remember the natural numbers. N plus 1 lives in there. Ooh. So add that over, then by distributivity we get this, but since a capital N plus 1 is a natural number, that means this thing has to be in the set, but that means it has to be less than or equal to alpha, and we get, oh hey, alpha strictly less than alpha. Like I said, you'd be surprised how often you explicitly use that fact. Pretty amazing. Alright, and then there you go, there's the proof. We're done. Beautiful. So here we go, our first actual instance of the least upper bound property showing up and verifying that something is true about the real numbers. If I have a positive real number, a strictly positive real number, and I add it to itself as many times as I want, I will eventually become bigger than any real number you can think of. And it turns out that that idea, which note we proved using the least upper bound property and some other algebraic facts here, has a lot of important consequences in terms of how natural numbers behave. Okay, so specifically, given any real number, there is a natural number strictly bigger than it. Given any positive real number, there is a 1 over n that's always smaller than it. Right, and that lines up with our intuition that the limit as n goes to infinity of this should equal 0. This should get arbitrarily small. So for any positive quantity, and here's our first let epsilon be greater than 0. Alright, and then finally, equipped with this, we can then prove that the set of 1 over n has 0 as its infimum. So here we see an infimum that does not actually belong to the set. Cool. So the natural numbers, good time. Archimedean property, even better time. Beautiful. Alright, so let's invoke the Archimedean property. Right? The math gods let you prove something, so you better use it. Alright, well, 1 is strictly positive, so the Archimedean property yields an n, so that x is less than n times 1, but multiplying by 1 gives you n, so there you go. For any real number, there is a natural number that is strictly bigger than it. So note, this implies that the natural numbers themselves are an unbounded set. There are arbitrarily large natural numbers. Beautiful. Alright. Similarly, for the 1 over epsilon, by the Archimedean property, by hypothesis, we can multiply this by n and eventually get bigger than 1, no matter how small this is. And then now n is greater than or equal to 0, which means it's strictly positive, so 1 over it is strictly positive, so I can multiply it across an inequality without causing an issue. Alright, okay. So, let's now use point 2 to prove that that set has 0 as its infimum, and this giving us an explicit example of a set with an infimum that is not, in fact, a minimum. Alright, so 1 over n is strictly positive because n itself is greater than or equal to 1, so 0 is a lower bound for the set. Let's say you take any lower bound. I want to prove that it is always less than or equal to 0, so suppose not. If it's strictly positive, then point 2 lets me find a natural number that is strictly less than it, which would mean that b cannot be a lower bound, which is contradicting my assumption. So it's got to be that b is less than or equal to 0, so 0 is the largest possible upper bound of that set. So 1 over n is bounded below by 0, and it's the biggest thing it's bounded below by. Beautiful. Cool. So, very neat. And here we see the Archimedean property being very clarifying. right? Revealing that the real numbers have these properties to them that we know to be true, but now we have got hard evidence, hard proofs explaining why things involving the real numbers work the way that they do. Okay, so next up, the set of integers. So, alright, so we've got the natural numbers. We are pretty friendly with them. So let's get into the integers. So note n for natural number probably makes a lot of sense. Z for integer might be interesting, but that's coming from German, the word Zahlen, which doesn't directly translate to integer, but good enough, right? The Z looks pretty fancy. So what is the set of integers? Well, what do we think about? Right, it's the natural numbers, 1, 2, 3, 4, 5, 6, so on and so forth, 0, and then -1, -2, -3, all those ones. So that's literally what it is. It's just that set. All right. That being said, there is a very powerful algebraic characterization of the integers, which lets us prove a bunch of facts about integers without having to go too nuts. Okay, so specifically, we're going to prove that every real number is an integer precisely if it's the difference of two natural numbers. All right, so you are an integer precisely if you're the difference of two natural ones. Okay. Well, suppose you are an integer. Well, then you are either a natural number, 0, or negative of a natural number. So there's 3 cases to consider. Okay, if you're a natural number, then n plus 1 is a natural number. So we set n to be x plus 1 and m equal to 1. The difference gets you to x. If you're equal to 0, then we just subtract off 1. Now, note, there's nothing here saying that this is actually a unique representation. Obviously, 0 can also be represented as 2 minus 2. Okay. All right, and finally, if you're equal to negative k, well, then we let n be 1 and m be k plus 1. And there you go. There we go. Regardless, if you're an integer, then you have to be n minus m for some natural numbers n and m. All right, now the only thing next to the proof, the sort of the trickier part of the proof, is suppose this holds, then you actually need to be an integer. So that's actually kind of the more exciting and interesting part. All right, and so if you let your mind flip back to when we were talking about natural numbers, I pointed out that there was a key ordering property that the natural numbers had. So indeed, 3 possibilities. Hey, trichotomy. So if m is strictly less than n, that means n is m plus k for some natural number k. X is n minus m, so that means x has to be k, which is a natural number, so x is an integer. Beautiful. If m is equal to n, well, then x is 0, which is an integer. And likewise, if n is less than m, well, then m is n plus k for some k out of the natural numbers, and so then x is equal to negative k, which is an integer. And there we go. Regardless, we have to be an integer. Beautiful. All right, so this is a wonderful characterization of integers, and it lets you prove pretty much any fact you want to prove about integers. So, for example, the sum of 2 integers remains an integer. All right, well, the only way you're an integer is if you are a difference of 2 natural numbers. Add these up. There you go. You're a difference of 2 natural numbers. The end. It's that simple. Beautiful. All right. Wonderful. All right. And also, this is another, by the way, justification of 1 being a natural number, because you do all these 1 tricks you're pulling here. Again, doesn't matter where you start the natural numbers, but for this one, I like it, having starting at 1. All right, and now, here we see that this characterization of integers lets you prove facts about integers pretty easily. And in fact, a whole bunch of other facts about integers can be proven using this characterization, such as the negation of an integer remains an integer, the product of 2 integers remains an integer, an integer is less than another one precisely when their difference is a natural number. An integer is less than another one, well, I'm allowed to add by 1 and I don't get any bigger, and likewise I can subtract by 1 and don't get any bigger. And my all-time favorite, if I have an integer and I've got a real number that lives between n and n plus 1, can't be an integer. Beautiful. So, like I said, again, we're not aiming to be exhaustive here, just eliminating. And so you can prove any fact about an integer you want using this. You can also use this to extend the definition of exponents to include negative numbers, of course, when defined, and so on and so forth. All right, but let's prove a fact about the integers now that is incredibly powerful. And that's something called the well-ordering principle, which says the following. Any non-empty bounded below subset of integers must have a minimum. So note, this actually implies that any non-empty subset of natural numbers must have a minimum. And also, once we prove this, then this is just following it. And again, here we'll see the least upper bound property is our friend. So this fact about integers, if I gave you a bag full of non-negative integers and said find me a minimum, you can. Here's the proof why that's true. All right, well, A is a non-empty bounded below subset of the real line. So, because least upper bound property guarantees infimums, that means we've got an infimum. All right. If I add 1, I get something strictly bigger. So that means this here is not a lower bound, so there's something out of the set that it's less than. I claim that this thing is in fact the minimum. So in order to be a minimum, I just need to prove that it's in fact a lower bound for A. All right, so take something that lives in A. If it's strictly less than M, then I can add 1, and I do not exceed M. And here we see that key property of integers showing up. And then now M is strictly less than alpha, so then you subtract off 1, but then we get N is strictly less than alpha, which contradicts that alpha is a lower bound for A. So it's got to be that M is less than N, which means that M is a lower bound, it belongs to the set, so it must be the minimum. And there we go. Beautiful. All right, and the well-ordering principle is a very powerful tool, especially when it comes to creating functions involving integers. So note, if you've got a non-empty subset of integers that's bounded below, it's got a minimum. If you let your mind flow back to like the very first slide of the course, I created a function using minimums. Ooh, I wonder if I use the well-ordering principle to create that function. All right, so let's actually see this in action. So, for example, we'll prove that, given any real number, this set must have a maximum. All right, well, well-ordering says all I need to do to verify a maximum is that we're non-empty and bounded above. All right, well, by the Archimedean property, I can find a natural number that is greater than negative x, which means x is greater than negative n. Negative n is an integer, so this set's non-empty. And that set's clearly bounded above by x, so it's not empty and bounded above. So well-ordering principle ensures that it has a maximum. Beautiful. So in fact, if you know your stuff here, this is actually the floor, the largest integer less than x. So similarly, you can also create ceiling using this. All right. Beautiful. Here we see a nice little application of the well-ordering principle, and let's actually push that further and prove the following. If I have two real numbers and their difference is strictly bigger than 1, there's got to be an integer that lives between them. Right, that makes a lot of sense, because if you think about, this is representing a distance of the space between two real numbers. Well, if it's bigger than 1, there's got to be an integer somewhere in there, because the integer cuts up the real lines into chunks of length 1. All right, now let's prove it. So let A be the following set, with the set of integers that are less than or equal to x plus 1. All right, well, we know that that has to have a maximum, so let n be the max. I claim this is the n we're looking for. So first of all, since it's in A, right, remember maximums belong to the set, it's less than or equal to x plus 1, and x plus 1, add the x over, is strictly less than y. So we have half of it done. So now, why does it have to be bigger than n? Well, probably because it's the maximum of A. But how would you prove that? Well, let's say that n was actually less than x. Well, then add 1 to both sides, so it would mean n plus 1 is an A, but n is the maximum of A, so it would mean n plus 1 is less than n. That can't happen. That would give you 1 is less than or equal to 0, so it's got to be that x is actually strictly less than n, so n strictly lives between x and y. Beautiful. There we go. Right, again, a fact that you knew about real numbers. If I told you the difference, but the distance between two real numbers is bigger than 1, you go, well, there's got to be an integer in between them. And now we've got a proof of it. Beauty. All right. Now, one last set to discuss is the set of rational numbers, which, right, you just define as follows. It's the collection of m times the multiplicative inverse of n, where m and n are integers. And this set can be proven to have all of the usual algebraic properties. You just manipulate the fractions, and note that the product of two non-zero real numbers remains non-zero, a product of integers remains an integer, the product and sum of integers are integers, and fractions work the way that they've always worked. Right, so note here I'm sneaking in s and s is multiplicative inverse, and here I'm sneaking in n and n's multiplicative inverse, and just combining them together. Right, so again, the rules for addition and multiplication still work, are now true. If you want to formally prove this out a little bit more, you could, but right, we know how fractions work. They work like this. And there you go. All right, so beautiful. We now have the rational numbers. They're this wonderful subset of the reals. They have all of the usual algebraic properties that you know, and you can prove them in similar manners, that they're closed under negation, they're closed in the products. 1 over a rational number is remaining irrational. But let's finish today off with one of the best proofs ever. The set of rational numbers is dense, meaning that if I take two real numbers, I can always find a rational that lives strictly between them. And the good news is that we've got all of the tools we need to prove this. And not only just prove it, really slickly prove this. Check out this proof. So, note, our hypothesis tells me that y minus x is strictly positive. By the Archimedean property, there is an n, so that n times it gets strictly bigger than 1. Oh, hey, this is a difference of two real numbers that's strictly bigger than 1, so there's an integer that lives between them, then divide by n, and the proof is over. Boom. Love that proof. That proof is so good. Right, and note, we got this proof by carefully working out all of the properties of the natural numbers and carefully working out the properties of the integers. Beautiful. Wonderful proof. I love this proof so much. All right. So there we go. We now know that the real numbers are, in some sense, the right set. They've got the integers, they've got the rationals. The integers and the rationals are behaving in ways that we know them to behave. The only thing now to do is that the real numbers also have all of our other favorite numbers in them, the irrationals. All right, that'll be our goal for the next video.